Hey everybody, in this video I wanted to talk about net ionic equations. That's the ultimate goal, but to get to net ionic equations we have to know a little bit about reactions, we have to know a little bit about solubility, and then finally when we're all said and done, we can finally get to a net ionic equation. So let's talk a little bit about solubility, even though I've talked about this in other points throughout throughout the course, I guess. What we know is that when sodium go here, when sodium is in water and when chloride is in water, the water is able to overcome the attractive force here by doing what they call solvating. And so you end up with water molecules here that are attracting the ions. Okay, and so what happens is in solution we have sodium ions and chloride ions floating around independently of each other. Okay, now what happens if we add silver nitrate? So here's the here's the neat thing. So we have some sodium ions floating around in solution, and we have some chloride ions floating around in solution. And just for completeness sake, I'm going to do this here. Okay. So these guys are all floating around. What I'm not showing here is the water in between everything. Okay. And now if we add silver nitrate, keep in mind silver nitrate is also soluble. So you're going to have some silver. Okay. And then nitrates floating around, okay, in solution, and then, okay, so that's cool. So now when we think about a reaction happening, we don't have these compounds, rather we have these ions floating around in solution. And yep, there's water solvating around the ions. So is there attraction? And I'll do the attractive forces in red here. Is there attraction here? Yes. But what happens when these two are attracted to each other? Well, they just kind of bounce off because the water is allowing this to act on its own. It's overcoming this. So they are attracted to each other, but no more than water is. Okay, what about an attractive force here? Yeah, well, there's not going to be an attractive force there because you need opposites to attract. Okay, what about here? Well, sodium is going to be attracted to this negative nitrate, but again, these guys are going to bounce off of each other and they're going to be soluble. If I write up here Na, and then this is attracted to here, sodium nitrate is also soluble. So this guy isn't going to do anything. Okay? And we know that silver attracted to nitrate isn't going to do anything because silver nitrate is soluble. But what happens here when the silver and the chloride get attracted? They don't just bounce off of each other. Silver and chlorine, when they get together, all of a sudden they like each other enough, they're attracted to each other enough that they form a solid. So silver chloride is a solid, and that's what this means. This is a state symbol. It's an S for solid. Guess what an L is? That's liquid. G is gas. And actually, AQ means that it's an aqueous solution. So here's the thing. And so silver chloride forms a solid, and that is not soluble, so this attractive force is not going to break by being in water. Okay? And so that's like the chemistry of what's going on here. Now, here are some notes that I may have alluded to previously, but I want to make sure that I say them explicitly. Okay, ions that are dissolved and soluble will act independently of each other. In that last example, sodium acted independently of chloride, which acted independently of silver, which acted independently of nitrate. Okay, they all were floating around the solution looking for something to happen. What this does, this independently acting sort of thing, that is represented by the total ionic equation. Okay, and then what ends up happening is some of these guys will react and some of these guys in the solution won't react. Okay, and so it turns out that silver ions, when they get close enough to chloride ions, will react and form a solid. Okay, and so that means that you have these guys, so you have Ag plus Cl minus, and that's going to form AgCl solid. And these guys are aqueous here because they're started off being dissolved in water. Okay, but what about the sodium and the nitrate? Well, those things don't change during the reaction. They stay ions, they stay floating around in our mixture, and those are called spectator ions. Okay? Those are called spectator ions. They're just looking at what's going on in the reaction, like spectators in a stand. Okay, at a football game or a basketball game or a baseball game. Okay? Or any other sporting event or competition. Okay? And the reaction that shows how the things react is the net ionic equation. The net ionic equation does not show anything that stays the same. It doesn't show any of the spectator ions. Okay? So let's do some sample problems and go through and actually write some of these guys down. Okay? Okay, so it says, write the molecular equation, total ionic equation, and net ionic equation for the following double replacement reaction. Okay, so this video is not about writing formulas, so I'm pretty sure that I left that off of there, though, so it should be lead 2 nitrate, and it's aqueous. So PbNO3 2. Now, aqueous, that's a fancy way of, well, first it gives us the state symbol, but it's a fancy way of saying that it does dissolve. Okay, that's a fancy way of saying that it does dissolve. So we know that what is going to happen here is that lead nitrate is going to split into lead ions and into nitrate ions. Okay, and then we have sodium bromide, which again, NaBr. That is also aqueous. Okay, and so now, what's going to happen in this reaction? Well, this is a double replacement reaction, so that means that we end up having a, I would call a wife swap. Okay, and so sodium nitrate, so we're going to form sodium nitrate, because sodium is going to go with nitrate, okay, plus PbBr2. Now, we don't know what the states of these are. We don't know if they're solid, liquid, gases, or aqueous, but we know our solubility rules. Remember, anything with sodium is always soluble. That's enough, so we should know that that's aqueous. If that's not enough in your own head, look at nitrate. Nitrates, all nitrates are soluble. So that means that that compound is going to be aqueous. We're going to find it aqueous. And then for bromides, I think that the way that I was showing you, it was like number 2 on the list, right? And so bromides are almost always soluble except for silver, lead, and mercury. And so this guy is going to be a solid. It's going to form a solid. Remember, ionic compounds have a tendency to form solids. Okay. And so then that's going to come out of the solution. Okay, so that right there is the molecular equation. It shows how the molecules are reacting. But we want to write a total ionic equation. The total ionic equation shows how the ions are acting. So what we're going to do, and kind of the shortcut is, any of these things that we see that are aqueous, we're going to split into their ions. Because what we know is that aqueous things are broken up by water, and that the ions act independently of each other. So the TIE, the total ionic equation, and I always run out of room whenever I do these things, but I'll give it a shot, okay, is Pb2 plus aqueous, right, because it's in water, plus NO3 minus aqueous. Okay, I know there's a 2 there. That just means there's 2 nitrates. So if you wanted to, you could put a 2 there. Okay. Plus, now, this guy is also aqueous. Na plus aqueous plus Br minus aqueous. So all this stuff that we've been dealing with naming and knowing charges, all of that comes back to haunt us now. Okay, reacts to form. Okay, it's a double replacement reaction. Okay, so now this is aqueous, so even this splits up. So this is going to be Na plus, and that's aqueous, plus NO3 minus aqueous, and then plus, there it is, I ran out of room, PbBr2 solid. Okay, now that's the total ionic equation. We wrote all the independent ions and what they're doing and how they ended up in the solution. Now we want to write the net ionic equation, so I'm going to do that, and in order to do that, I'm going to erase this guy here. Okay. And so to write a net ionic equation, it becomes actually pretty straightforward once you have the total ionic. So for the net ionic, and I'll do this in black, for the net ionic equation, what we're going to do is we're going to cancel out anything that's the same. Okay, so if we look, the example that I have is sodium plus here and sodium plus here, they're both aqueous, nothing changes. So that indicates that this guy is a spectator. Remember that the net ionic only wants to deal with the things that change. Well, in this case, the things that change are the lead and the bromide. Look here, this is lead 2 plus ion floating around aqueous. Over here, it's lead bromide, and it's part of this solid. So that definitely changes. So we're going to do that. Pb2 plus aqueous plus, and now let's see here. Notice that the nitrate also stays the same, so that's a spectator. These two things are spectators. I kind of cancel them out. Okay. And then the bromide is there, Br, and then that's Aq, and that reacts to form PbBr2 solid. Okay. So this is your net ionic equation. And so that is what we're trying to get at. So that's the example using a double replacement reaction. There will be another example that I'll get to that talks about single replacement reactions, but not for this video. Okay, have a great day, and Stay out of trouble.